Okay, hopefully everybody can hear me well. So hi everybody, and today my name is Arthur. I'm a first-year PhD student in Germany, and today I'm going to be talking about relational properties in the context of legal expert system. So first, a bit of context and motivation. I think it's clear to everybody in this room, and that's the very reason of the existence of this workshop, that software systems are increasingly used in legal procedures, such as computing taxes, attributing social allowances, etc. And of course, a very natural question to ask, and this question has been asked several times this morning already, what about the correctness of such software systems? In particular, are they faithfully implementing the law? Are they fair? Are they secure? All that sort of questions. In a more general context, in the context of a software system, this is very similar to the question of functional correctness of a program. So we want to prove something like for all input, the program is computing the expected result, whatever expected result means. And this is actually the main concern here. So to do that, we need to know what is the expected result. And it turns out that it's very difficult to apply in the context of legal expert system because we do not really have a clear formal specification of the correctness, or at least we do not always have this component. So how do we still assess the reliability of the system if we do not have such a clear specification? So we will have to find all the correctness criterion, some sort of robustness criterion. So the initial problem is that we do not have a clear one input versus one output specification to verify. So one solution would be to say, okay, let's compare several outcomes of the same program on different inputs instead, and maybe that's enough to test some robustness criterion of the given system. And this leads to a more relational kind of specification. So there exist already a lot of examples of such relational specification, in particular in the example, with the example of tax computation. So I put here two examples. One is from this paper, Metamorphic Testing and Debugging of Tax Preparation Software, that says, well, for two individuals that differ only in age, well, the federal tax return of the older individual must be greater than or equal to that of the younger one. This is the kind of relational property we would like to prove. Similar properties have been found also by Denis-Mérigoux. Okay, so relational property in general. So we just saw that they occur very naturally if we want to verify the robustness of legal expert systems. So in a more general setting, those relational properties have different names depending on the field of application. So sometimes they're called relational program properties, sometimes metamorphic properties, hyperproperties, depending on the community that you talk to. But they all have a common characteristic. They compare several executions of the same system, and this makes them significantly more expensive to verify than classical program properties. But how do we verify them anyway? Because we really want them to be verified. So even if it's hard, what can we do? So one approach is to do statistical testing. And this approach has been presented in this paper. So we start with an informal property. We formalize it in a logic, for example, Forstadel logic. We can see that here it's indeed a relational property. There is just like comparison of the two outcomes of the same program. And the methodology they propose is to just statistically find inputs that violates the property. So some sort of like testing mechanism. The limitation of this approach is, of course, that you won't prove that there is no bad pair of inputs. You will prove that eventually you have a counterexample to the relational property, but you don't prove that there is an absence of bad behavior. So how do we prove that there is no bad inputs? That's the question I'm trying to answer right now. What we could do is to do it by symbolic execution. So we start with the same specification, so a relational formula that quantifies over two separate inputs. And this time we're going to assume that we do have access to the program, to the source code of the program that computes, for example, a tax return or something. So I took a very silly example. So what we can do is to execute this program with like a symbolic input, do symbolic execution, and collect the possible outcomes together with the past constraints that leads to the given outcomes. So now, once we did that, what we can do is simply like compute all the pairs of possible outcomes and characterize the possible violations of the relational property. So if we do that, we have, like in this very specific example, nine examples, possible violations. And now if we send all that to an SMT solver or to any automated prover, well, if the prover say it's satisfiable, we found a bad input. If it says it's unsat, we have no bad inputs. And we're very happy because we just proved that the relational specification is met. Okay, so now that this has been said, what is next? How do we apply those ideas in practice? So what we would like to do is to develop a specification language to write relational properties as encountered in the context of legal systems, especially tax computation. So this would mean having a simple syntax, built-in abstraction that are specific to the field. The next step would be to integrate an automated verifier for such properties for this logic inside a given platform, and in particular inside the ProLaLa' platform. Why doing that? Simply because it would be hopefully much more efficient to target such a domain-specific language than to target a general-purpose programming language, for which we know that verifying relational properties is incredibly hard, and there is very few mainstream software to do that, actually. Okay, some other, it's a little bit outside of the scope of what I was discussing today, but still some interesting things an interesting thing to note is that there is other form of relational properties that talks about time, for example, and those could be applied also to legal expert system. For example, some fairness property or non-interference property in the context of e-voting platform could be expressed using more temporal relational logic, and that's also something we would like to investigate in the future. Thanks.
Hello, thank you. Great talk. You mentioned that you're limiting it to ProLaLa', or you're so I'm not a computer scientist, just FYI. You said that you're limiting it to taxation. Is that correct?
Yeah.
I just wondered if you have any idea about potential broader applications for what you're proposing here, and what the justification would be for going further than that, if you have a broader.
So you mean, like in a general context, like
yeah,
for
like
any other kind of, yeah.
From a perspective of the law,
yep.
Where are you drawing the limits of this kind of application, essentially? Is it just tax? Can you see a scope for broader application, or what?
I think the problem still is that you need a clear specification to verify. I'm absolutely not an expert in legal systems. I'm new to the field. I don't know if such a specification exists in all the cases, and I think it might be hard to find. However, I already have in mind a couple of applications where we do have some clear robustness criterion that we want to assess. One very common example is the e-voting, some e-voting platforms, where you do have, like, if you view your e-voting platform as a reactive system, where you have like several inputs at different time points. Those inputs are typically the vote of the different people that are using the platform. You want to prove some property like invariance of the result of the outcomes of the election with respect to the order of the vote, that sort of property. So that would be another application of relational properties, in particular temporal relational property, that we could investigate. Yeah. However,